Fine. So let us continue. So McCulloch-Pitts neuron model was formulated by Warren McCulloch and Walter Pitts in 1943. It is quite a old invention, and it actually continued till late 80s to evolve as the learning machine. But in somewhere in 80s, the neural network itself was almost a dead field because we were not having supercomputing power to process such kind of data. But later on, with the invent of very high-speed processors, we were able to process the data at the neurons, and then the entire science revived, and we were able to do a lot of machine learning and lot of deep learning even with the neurons. The initial model was designed to allow only the binary states 0 and 1. The connection path can be either excitatory or inhibitory. The excitatory connections have positive weights and inhibitory connections have negative weights. Which weights do we get actually will depend on our training data, what we want our system to learn. So now we had implemented logic through the neurons, and these the number of neuron at the processing level is single in the case of and or, right? We were able to work with a single neuron. You can see how simple the model is. Now we move towards a bit complex problems, and the complexity comes in terms of laying a decision boundary. Even when you recall your understanding of the classification, where we were actually trying to visualize the objects or classes data as simple n-dimensional points, right? And then the challenges there were to obtain the decision boundary. More complex the decision boundary is, more complex you would see the neural network structure is. Let us look at this example of exclusive OR. Here we try to plot the two-dimensional pattern on a two-dimensional Cartesian plane and plot a symbol appropriately for both 0 and 1 outputs. How would we even design this, right? Let us look at this data. What the data should be? The data will be something like this. If I am taking x1 and x2 and their actual output y, we will have exclusive OR is something defined as 0 0 being 1. Okay, no, it is 0 and 0 and 1 being a 1. Exclusive OR means you have a output as 1 only if any one of the inputs is 1, right? So then this is 1, and then if both the inputs are 1, we do not classify it as output 1 and we classify it as 0. Have you understood the data? The exclusive OR data? Yeah. So Anirudh, you want activation function detail regarding the OR input? Am I right? So the activation function in the previous example, I had shifted from the threshold value being 1.5 to threshold value being 0.5. It actually carried forward your own model, but with a different threshold. That makes sense? Is it okay? Or should I explain it again? Fine. So only by changing the threshold, we were able to classify it with 0 error. Later you will see that this threshold makes a very important input in the neural network which we attach to the processing neuron, and we would call this W0. Later on we will see that W0 actually is anything which is related to the threshold. Of course, you can say that W0 is a kind of negation of the threshold, and we call such kind of W0 as bias. Right, so we will come to this kind of discussions later on if it is required. So I'm coming to the model that is required for understanding the need of more than one neuron. So exclusive OR simulation, here x1 and x2 are taken as 0, 0, 0, 1, 1, 0, 1, 1, but their output, expected output or actual output is 0, 1, 1, 0. Is the data clear? How different it is from OR input? Here, the fourth data, 1, 1, doesn't get a Y as 1. Here we are going for an exclusiveness. If both are 1s, then we do not consider it as 1. Okay. Now, if you try to plot it on a two-dimensional space, can you plot? So, I would expect that you plot it on the two-dimensional space. Represent the 0 class as a cross and represent the class 1 as a circle. Can you do that? Anybody is getting the detail? Now, can you separate the data belonging to the two classes by one line? Anyone, please respond. Yes? Yeah? So, Venkat has responded that the data is not linearly separable. Right? We cannot separate the data by one line. So, what do we do? Here, we have this data. I am going to draw this for you. So, just a kind of simple representation. I am taking different colors, say red for this input 1, 1 and 0, 0. Okay. Then different color, I am taking green for 0, 1 and 0 and 1, 0. So 1, 0 and 0, 1, they are representing class 1, while 1, 1 and 0, 0, right? So 1, 1, x1 and x2 being 1, 1 and x1 and x2 being 0, 0. They are represented by blue dots, and the data 0, 1 and 1, 0, they are represented by green dots. So green dot is representing the class label as 1 and the blue dot is representing the class label as 0, right? So we cannot separate out these two by by one single line. I may have this, right, but this is separating with the classification error of 2. Another line, this is again separating the data by an error. If I make this line, the third line which I am drawing, it is still inclusive of two mixed classes. That means if I am having if I do some more changes, let me remove these lines. Okay, and I have one line here, okay, another line here, then we are able to separate the data into two separate classes, one which only includes blue samples and another which includes only green samples belonging to the class 1. So here you can see a simple correlation between these boundary lines, okay, and the number of neurons. If I am able to separate the data using two straight lines, then we can make use of the two neurons and it will be able to give me the classification correctly with no classification error. So for you, the homework is that you work out things with a single neuron first and try to adjust W's for making their combinations, maybe 20 different combinations you try to find Y for all the 4 inputs in such a way that you get a 0 error. Will you be able to do that? Will again depend on how much you are putting efforts in finding the weights. But in any sense, we will not be able to work out the classification with single neuron. And if you work with 2 neurons, you are sure to get 0 classification error, and the testing samples will also get correctly classified. Let us see. I could take some exhibitory, excitatory neurons and some inhibitory neurons with minus weights. There is always a possibility that you can have negative weights along with the positive weights. Suppose we take 1, -1, -1, 1. The terminology actually says that if this is your first neuron and this is your first neuron in the previous layer, right? So then this weight W is known as W11. So the second neuron in the input layer and the first neuron in the processing layer, the label of the weight of that synaptic link would be known as W12. Like that, there is a simple terminology. So what do we get? W11, W12, W21, W22. So if you work out f of n1, what will you get? N1 is actually the weighted sum. So if I'm going back here, you can see that the names of these W's are W11, W21, right? And then this one is W12 and W22. Okay, W11 relating the first input neuron to the first processing neuron, W21 relating the second processing neuron to the first input neuron, right? So the next layer's index comes first and the previous layer's index of the neuron comes second. That is the simple terminology which is normally followed in defining the weights. So picking up that same terminology, you get these weights W12, okay, W11, W12, W21, W22. So what is this N1 going to be for X1 and X2 being 0? It is actually the weighted sum, and the weighted sum goes out to be 0. N1 is the output of the previous first neuron. Okay. So N1 is the output of the first neuron, N2 is the output of the weighted sum of the second neuron. Not the output, but the weighted sum. Okay. So what will be the name of the weight connecting the first processing neuron with the second input in the previous layer? It will be W. Can you tell me? Yeah, W12, which I have mentioned also. Now, the first neuron in the input layer and the second neuron in the processing layer. How would you label this? This will be W21, right? And the second neuron at the input layer and the second neuron at the processing layer would be called as W22. Okay, so you have understood this? So now if your W11, W21, W12 and W22, these are given, right? 1 -1 and -1 1. Can you find out? This is 1 minus 1 and minus 1 1. So what will be n1, the weighted sum? What will be n1 for 0 0? I'm taking x1 x2 here. X1 is equal to 0 and x2 is equal to 0. Then what will be my n1? Okay, and what will be my n2? Can you tell for 0 0 with these weights? What is it that is contributing to the processing levels neuron 1? It is the first input x1 and the second input x2 through their weights w11 and w12. Right? So what is the expression for n1? Can you tell? Sorry. Yeah, anyone? For x1 equals 0 and x2 equals 0, what is the expression for n1? It is w11 x1 plus w21 into x2. Am I right? So then we substitute the values. What is the value of w11? It is 1, right? So 1 into 0, okay, plus what is the value of w12? Sorry, no. This one should be w12. So I must correct it. w12 star x2. Okay. I'm only referring to the first neuron at the processing level. So this is equal to 1 into 0 plus minus 1 into 0. Am I right? So this gives me 0. So n1 is actually 0. Okay. Now what is the expression for n2? The second neuron's weighted sum. Second neuron's weighted sum is equal to w21, okay, x1 plus w22 into x2. Okay, so you can put the star in between. This is equal to, what is w21? W21 is minus 1 into 0 plus 1 into 0. Okay, so n2 is actually also 0. Now you have to define two activation functions, the one which triggers the output from neuron 1 and the other which triggers the input from neuron 2 as an output to be received at some neuron, say neuron 3. Okay. So what will be your activation function for n1? You want a output to be equal to 0. Right? And there should be some more weights. I would say that these weights are, let us say, W. Sorry, this one should be neuron 3 basically. I must clean it and write again. This is neuron 3. So when you are connecting these outputs from neuron 1 to neuron 3, let me call as 3-1 and this one as W 3-2, right? So this terminology may help. So Amit, the makeup exam will also be having the same syllabus as it was there in the regular exam. So today's topic is the post-midsem exam syllabus, right? So this will be the part of your comprehensive exam, fine? Okay, so can you suggest the activation function that triggers N1 to be added at neuron 3? When do you want to trigger N1 as 1 and when do you want to trigger N1 as 0? And then also at the same time you may have to pick up W31 and W32 also. Suppose I take W31 as 1 and W32 as 1, then what should get added for us to give us a Y value of 0? Say for example, I trigger this only if I am finding f of n1, right, to be greater than some threshold T1. Okay. If I'm taking T1 as 0.5, this itself is a 0, so I get something like f of n1 as equal to 0, right? Similarly, if I'm taking the similar mechanism for triggering the output from neuron 2, you get f of n2 greater than T2 being triggered as 1, right? So you have to define your function, but I am taking some hint from this to trigger f of n2 as equal to 0, right? Because my total weighted sum at neuron 2 is also 0. I don't want to trigger this. Basically, it has to be triggered only as 0 and get weighted sum at neuron 3 as 0. 1 into 0 and 1 into 0, that gets us 0. So then there is a need also for us to define a new function here, right? Of course, the function name can be changed from f to g for the second neuron, and for the third neuron, you can say f is my function for neuron 1, g is my function for neuron 2, and h is my function at neuron 3. Okay. So let us look at this computation, right? I'm taking f of n in general as 1 if n is greater than or equal to 1. Here I'm taking the threshold for both the neurons 1 and 2 as 1. So because you have n1 and n2 both as zeros here, which is we just calculated. Okay. So f of n1 will be 0 and f of n2 will be 0. And what we want is 0. Similarly, for 0 and 1, with the same set of weights 1 minus 1 minus 1 1, we get the value of n1 as minus 1 and of n2 as 1. So f of n1 will be 0 and f of n2 will be 1, and it gives us a 1, right? Similarly, you apply the same logic for the remaining two inputs, and you get exactly the predicted output same as the actual output, right? So f of m is actually the same as that of y. So with these two neurons, you are still able to get training error as 0, right? So there is a important thing called as activation function, which is very important in the design of neural networks. These activation functions trigger the received weighted sum of the input according to the expected output. Let Gn be the activation function, where n is the summation of Wixi. So based on the value of n, the Gn is triggered, and then different activation functions are different. Activation functions can be step function, as we discussed. It could be linear function as simple as y equals x, and the sigmoid function, which is more used for the regression many times. So step function is simple. Gn equals 1 if n is greater than t, and is 0 if n is less than or equal to t. The output is always 0 or 1. And it is actually useful in pattern recognition, where an output 1 can represent the class which the input test pattern belongs to. We will have one simple example of a 4-class classification problem, and we will see how we can model the output as 1 and 0, despite the fact that we have 4 classes, right? So if we have two discriminatory features as color and texture for automated route recognition, let us code the attributes as 1, 2, 3 for red, orange, and yellow colors respectively. And let the textures be defined as 1, 2, 3, representing the degree of smoothness in increasing order. It is just a sample where we do not want to go for more realistic data, but just we are trying to pick up the features, okay, and define their outputs. Output is nothing but the actual class label. So then there are 4 different categories: apple, mango, orange, and plum, defined by their color and texture. So I could have, defined a neural network with a single output line Single output line could have been designed to produce a value 1 to represent apple output, 2 to represent orange, and so on. But it is actually very difficult to produce such complex output as 1, 2, 3, 4. Rather, it would be much easier for us to define our output as the 4-lined binary outputs, 1, 0, 0, 0 or 0, 1, 0, 0 for a different class. So here you can see that second output line should produce a 1, trigger 1 out. Remaining other lines should be silent. So I could even imagine a situation when I'm working with 4-class classification problem, working with the single neuron, let us say. Single neuron can also produce 2 outputs, right? Or maybe you have 2 neurons. You can understand 4 classes cannot be separated by one single line. So try to relate the number of lines, decision lines, with the number of neurons. So number of neurons, if they are 4 or 2, then you can still work with 4 different output neurons. So rather than making the same model as we did in the previous example, I could go for 2 different lines. Okay. Each one is specifying a 0 or a 1 output. Okay. Then I would have started classifying my output not just as 1, 0, 0, 0. I would have said that my apple class should be represented by the bit string as 0, 0, where I would expect the first output line to represent a 0 and second output line also to represent a 0, to produce a 0. Similarly, for orange, I should get something like 0 and 1. For plum, I should get something as 1, 0. And for mango, I should get something like 1, 1, or differently. That means 2 bits can also be used to represent 4 classes, and it is much easier to get the results in these 2 output lines than just a single line producing 1, 2, 3, and 4 for different inputs, right? Say for example here, smoothness and color are taken. So you know that these are the data which are separable through 2 lines, right? So these are the 2 different lines which can separate out the 4 classes. We can very well work with a linear set of boundaries represented by 2 different neurons, right? So when we train the neuron, we select the activation function first. A simple step function simply gives 0 or 1 and is not sufficient to produce output for 4 classes, as we have seen in this example. So we use 2 different neurons. Okay. Yes. Yeah. So Shrikant, what is your query? So that is up to your convenience which exam you write, right? Yeah. So do not worry, we take care of all the equality of the difficulty levels, right? So you please appear for your exam, okay? So here we are talking about these 2 neurons, and these 2 neurons are basically representing the boundaries, right? Output modeling, you can go with 0, 0, 1, 0, 1, 0, and 0, 1. Okay, here you should correct this. It should be 0, 1 in the third, and 1, 1. This represents the test input. Okay. So parameters for each neuron would be different. Whether you select a step function for neuron 1 and a sigmoid function for neuron 2, it all depends on your outputs and how you are modeling your entire training. Then there is a threshold that you want for each neuron, the weight for each neuron. So you can understand that there are three different parameters required for neuron 1 and three different parameters for neuron 2. Okay. So the training is supervised in nature. Neural network learns from training examples. Knowledge is captured in terms of weights. And then learning algorithms require the initialization of weights which later adapt to other examples. And you've already seen that learning algorithms are evaluated for their performances about how they are capable of responding to the unseen data. Okay. So gradient descent is the most popular learning algorithm. And of course, it has its own limitations, but this is the one which gives you a way to systematically and algorithmically find the best weights, right? On neural network architecture, it is actually about the arrangement of neurons along with the number of neurons. How many neurons should be there? How many layers should be there? Which activation functions should be associated with the neurons? And the input and output, along with everything, it constitutes the architecture of the neural network. So different architectures include feed-forward neural network. It represents a function of its input. And there are two different types of feed-forward neural networks. One is single-layered, another is multi-layered. And then backpropagation neural network, basically it is an algorithm that feeds its output back into its own input to get the weights modified. Okay. Yes, so here activation functions could be like this: linear, y equals x; logistic, which is y equals 1 by 1 plus exponential value of minus x. Likewise, there are different many. Initially, we work with the simple step function for the classification. Different regression problems, we can go with several other real valued functions. Okay. Feed-forward neural network will have all these inputs here, x1, x2, xn, etc. And then you will have multiple number of layers, the first hidden layer, second hidden layer, etc. And you can see that there are lines connecting these neurons from one layer to another. They are representing the synaptic weights. So the information is propagated from the inputs to the outputs, and in this particular model, time has no role. There is no cycle between output and input, right? So this is one form of feed-forward neural network. Then there comes a recurrent neural network. Okay, so in this we can have arbitrary topologies. Of course, this is a very difficult and complex level of network which is used to handle very complex problems. Then it actually can model systems with internal states. Delays are associated to a specific weight. Training is more difficult, right? So of course in this course we will not be working with such recurrent neural networks, um, but of course I would expect that you learn simple neural network models, right? So the performance may be problematic, the stable outputs may be more difficult to evaluate, okay? And they actually display a very unexpected behavior, the oscillation, chaos. So these are all the networks which you understand only when you have implemented many simple networks, okay? So with this, I'm stopping today, and in tomorrow's class, we will be talking about the gradient descent algorithm and a few more concepts of neural networks. Okay, so if you have more questions, you can ask. Yeah. Okay, fine. So no more questions. So I'm stopping it here, and we will meet tomorrow. So have a nice day.